Hi friends, we are discussing a topic in the muscle. It's related to the strength of contraction of a skeletal muscle, and we will see what are the factors that influence the strength of contraction of a muscle. Uh, as a medical person or a healthcare professional, many of you might eventually take up sports medicine or related branch, and where this question might come up that an athlete or a sports person who requires to produce strong contractions of the muscle, and the athlete would inquire, or the person would ask you this question: how can I produce my best possible contractions in the event, in the sporting event or the competition? So from that point of view, we have to understand what are the various factors that govern, that determine and influence the strength of contraction of a skeletal muscle. Why did I decide to take up this topic? Is because I observe most of the authors have not given these factors at one place in their chapter. These factors have given in a separate manner at different places in the skeletal muscle physiology. So therefore, it's important to understand all these factors together. So let's first enumerate these factors. Length tension relationship. That's the first factor, and we will then describe these factors in detail. Second, frequency tension relationship. Well, when I say tension, I mean the strength of contraction here. As you all are aware, we have discussed this before, that when the muscle contracts, two things happen in the muscle when it contracts. The tension is built up in the muscle and the muscle shortens. I mean, these are the two aspects of a muscle contraction: tension generated and shortening of the muscle. So when I say length tension relationship, it means how the length of the muscle determines the strength of contraction, the tension that is built up in the muscle. Then effect of load on the strength of contraction. Then fatigue, and then uh, motor units, number of motor units in a muscle, and number of muscle fibers in each motor unit. So these are the factors that in a broad sense govern the strength of contraction of a muscle. Let's just finish this. Number of muscle fibers in a single motor unit. So let's look at these factors one by one. Let's take the first one, length tension relationship. What we mean here is that strength of contraction is governed by the length of the muscle. So length tension relationship, and here the first thing that we say is about an important physiological principle, and that is Starlings Law. So it's the Starlings Law which we need to understand in this context. Look, there will be many events in which the sports person or the athlete might want to generate single best strongest contraction, just one contraction but strongest contraction. There are many sporting events, javelin throw, shot put, or high jump, long jumps, and so on. So what is it that can generate the single strongest contraction? This one question you might face as healthcare professionals. Let's try to understand this length tension relationship. So, length of what? Length of the entire muscle or length of the muscle fibers in it, or inside each muscle fiber there are basic units of the muscle called as sarcomere, length of the sarcomere. It governs the tension generated in the muscle when the muscle contracts. Starlings law says that within physiological limits, greater the initial length of the muscle, stronger will be the contraction and greater will be the tension generated. So, within physiological limits, remember this is an important first part. Within physiological limits, greater the initial length of the muscle, stronger will be the contraction. Stronger will be the contraction of the muscle. And that means greater tension generated. Stronger contraction means greater tension generated during the contraction. That's the Starlings law. Now, initial length means what? Initial length means when the muscle is beginning to contract. What is the length of the muscle fiber? Greater that length, stronger will be the contraction that is generated. But of course, within physiological limits, this law applies. So, initial length of the muscle has muscle fibers, therefore, initial length of the muscle fiber, or inside the muscle fibers, sarcomere. So, initial length of the sarcomere, right? And therefore, greater the initial length of the sarcomere, stronger will be the contraction. Now, what is the normal resting length of the sarcomere? The normal resting length of the sarcomere, which is generally referred to as length initial or length resting, it is about 2 microns. On an average, 2 microns is the length of the sarcomere. So, now imagine you stretch the muscle, increase the length, okay, muscle is in a resting state, stretch the muscle, increase the muscle length. That means increase the muscle fiber length, muscle fibers within the muscle, their length increases, and that means inside the muscle fibers there are sarcomeres, sarcomere length will also increase. So, for 2.1 microns, stronger contraction, 2.2 microns, even stronger contraction. What happens here is that within the muscle fibers there are sarcomeres, and sarcomeres are made up of an interdigitation of thin and thick filaments like this. And when you stretch the muscle and you stretch the sarcomere, what happens is that there is optimum interdigitation between actin and myosin filaments or thin and thick filaments. It becomes optimum, and to generate contraction from that is easier, or it produces stronger contraction. So, greater the initial length of the sarcomere, stronger will be the contraction because of this optimum interdigitation, better sliding of the thin filament over the thick filament. Now, this 2.2 microns is the physiological limit which we are referring to. 2.2 microns will generate the strongest possible muscle contraction, and therefore, it's called as length optimum. Optimum length of the sarcomere, which will generate strongest possible muscle contraction, strongest contraction, greatest tension development. Physiological limit reached. Now, if the sarcomere length increased further, means muscle stretched further, what contraction will it generate? No, the contraction will become weaker beyond this. Physiological limit has been exceeded. Now, what happens here is that if you stretch the muscle further in its resting state, the resting length has increased. What happens further is that optimum interdigitation now is lost. The interdigitation between actin and myosin filaments in the sarcomere, it will be lost. So, from that length, generating the tension will become slightly difficult, and therefore contraction strength will reduce if you increase the length beyond this point, and therefore 2.3, 2.4 microns, weaker and weaker and weaker contractions will happen. From that length, if you cause the muscle to contract, the contractions will be not strong, they will become weak. So, this is the interpretation of the Starlings law based on the sarcomere length. This is the physiological limit, 2.2 microns. Therefore, that length of the sarcomere is called as length optimum. It will produce strongest possible muscle contraction, and if you stretch the muscle fiber further, muscle and muscle fiber, sarcomere length increases, and that will not produce stronger contractions. And what is L max? Length maximum for the muscle and length maximum for the muscle fiber and sarcomere, it's about 3.65 microns. At this length, there will be hardly any contraction because you have stretched the muscle so much that the actin myosin interdigitation is lost completely. So, from that length, if you try to produce the contraction, there will be very weak contraction, virtually zero contraction. So, that's a interpretation of the Starlings law. Let the muscle stretch slightly to increase its resting length, increase the sarcomere length, and then produce the contraction. It will generate a stronger contraction. That was the first factor that influences the muscle contraction. Let's move on and see the next factor. As I mentioned, frequency tension relationship. Frequency of what? Frequency of stimulation to a muscle. Greater that frequency of stimulation to a muscle, what stronger will be the contraction. Let's see this relationship. Frequency tension. Now, before we actually understand this relationship, let's first learn about one single isolated muscle contraction, and we will take the things from there to understand frequency tension relationship. Let's imagine this is a nerve muscle preparation, a piece of vertebral column and the nerve that comes out, and this is the muscle. Now, we stimulate the muscle, we stimulate the nerve, and it sends impulse to the muscle, and the muscle contracts. The muscle contracts means it shortens. This muscle will shorten. Now, this one single contraction followed by relaxation of the muscle, relaxation will be lengthening of the muscle. Single isolated muscle contraction is called as simple muscle twitch. Now, this twitch, we will record it on a drum. So, what we actually are going to achieve is we will record one single isolated contraction followed by relaxation. So, this muscle is connected to a writing lever. Muscle is connected to a writing lever. This is just a diagrammatic representation to make you understand how we obtained a particular graph. Muscle contracts, the writing lever goes up. The muscle relaxes, the writing lever goes down. So, one single contraction followed by relaxation, where the writing lever going up once and down once. we will get a record like this. But this will not tell you anything. This will not give you much information. Therefore, what we do next is we will record this event on a revolving drum, rotating drum. In physiology experimental labs, we use a Sherrington Starling drum or the rotating drum. So we are going to record that one single contraction, isolated contraction followed by relaxation on a rotating drum. Now imagine this is a rotating drum. The writing lever going up and then coming down. This is getting recorded on a revolving drum. The event will now be recorded like this in a form of a simple curve. The writing lever going up and then coming down. Now we will obtain a curve. So that is how a simple muscle curve is obtained. One single isolated contraction followed by relaxation. Let's take the things from there onward now, that we have obtained a single isolated muscle contraction in the form of a simple muscle curve. So we applied the stimulus at point A, then the drum moved forward, and from the point B, the contraction started, the writing lever went up, then relaxation occurred, so writing lever came down. Therefore, this is the event of single muscle contraction and relaxation. BC is the contraction period, CD is the relaxation period, the writing lever coming down. And one more thing that you must note is that the height of contraction, height of this curve indicates strength of contraction of the muscle. You see, if the muscle contraction was stronger, the writing lever would go up higher. It will go up higher. That means height obtained will be greater. So greater height of this curve means a stronger contraction of the muscle. Remember, height of contraction indicates, height of the curve indicates strength of contraction of the muscle. Now, so far so good. We gave one stimulus. We obtained one single contraction followed by relaxation. Fine. Now, next what I do is I apply two successive stimuli. Two successive stimuli were applied to this muscle. Two quick stimuli, one after the other. What do I get? Two contractions followed by relaxations. Right. I get a record like this. Two contractions. Oh, but what do I observe here? All the things were kept constant. Everything was held constant, and instead of one stimulus, I applied two successive stimuli. I got two contractions. But what do you observe here? Quite a striking feature, quite an obvious feature is the second contraction has got greater height. All by itself. We did not change anything, just applied two stimuli instead of one. The second contraction was stronger by itself automatically. So, strength of contraction increased automatically for the second time. Now, this is called as beneficial effect, or this is said to occur because of the beneficial effect. This is said to occur because of the beneficial effect. Look, we are talking about the frequency tension relationship, frequency of stimulation to the muscle, and what bearing does it have on the strength of contraction of that muscle. So when I stimulated the muscle twice, the second contraction, and twice in quick succession, one after the other, very quickly stimuli were given, second contraction was automatically stronger. And why was that? That's beneficial effect. Now, the reason is said to be, or there are two reasons, two mechanisms that this happened. One is, there was, first of all, let me just say what is this beneficial effect? What do I mean by beneficial effect here? By beneficial effect, I mean that due to first contraction, some changes happened in the muscle which were beneficial for the second contraction, and therefore second contraction automatically became stronger. That's the meaning of beneficial effect. First contraction produced certain changes in the muscle, and those changes made the second contraction easier and stronger. Therefore, it benefited, first contraction benefited the second contraction, if of course stimuli were applied quickly, one after the other. Now, what were those changes that happened in the muscle? Two important changes what we must note. One is increased temperature in the muscle caused by the first contraction. First contraction increases the temperature in the muscle. You know, muscle contraction generates heat. So, temperature increased. And because of the increased temperature, the second contraction which followed had a better actin mass interaction, and all processes related to the contraction could be faster and easier for the second time because of the increase in the temperature. You know, we have discussed the diffusion and all the events related to it. Increased temperature increases the rate of reactions and the rate of diffusion, and therefore most of the events will be easier and strength of contraction will be greater. That's what one reason. And second is decreased viscosity in the muscle. Decreased viscosity in the muscle caused by first contraction, and therefore the second contraction became stronger. See, there are thin and thick filaments in a sarcomere, and thin filaments slide over the thick filaments. That is what is muscle contraction and shortening. Now, they are within a sarcoplasm. This inside the muscle fiber, there is a sarcoplasm, cytoplasm of the fiber. And that sarcoplasm, the cytoplasm of the muscle fiber, in which there are these thin and thick filaments, that sarcoplasm has a certain viscosity. So, first time sliding, first contraction of the muscle and first sliding of the thin filaments caused a decrease in the viscosity of that sarcoplasm. And if the viscosity has decreased, then the second contraction, the second time sliding of the thin filaments will become easier. So, decreased viscosity of the sarcoplasm, decreased viscosity of the cytoplasm inside the muscle fiber will cause a second contraction stronger automatically. This is the so-called beneficial effect. I have taken the important points only, important two reasons why this will happen. So, remember, first contraction, sliding of the thin filaments in the sarcomere, due to which the viscosity of the cytoplasm, viscosity of the sarcoplasm decreases, and therefore second contraction, the sliding will become easier and contraction will become stronger. Now, I go further, and instead of 2 successive stimuli, now I apply 5 quick stimuli, one after the other. Remember, what's important is quick stimuli, the stimuli given in quick succession. I stimulate the muscle now 5 times or 10 times in a second, quickly. What do I get? I get 5 contractions. Yes. And the graph now will be something like this, 5 successive contractions. What do you see here? Now this is this is along the expected lines, that I am getting 5 contractions. Each succeeding contraction is stronger than the preceding one. See, height is increasing with each next contraction. That means the contractions are becoming stronger and stronger and stronger. So, these were 5 successive stimuli, or if you give 10 stimuli, you will get 10 contractions like this. Now, this has been called as staircase effect. This has been described as the staircase effect. This term was put forward by Bowditch, or it was called in German, it was called as Treppe, and the Treppe means staircase. So this is called as staircase effect. Now, what is the reason? You can see the contractions are becoming stronger and stronger and stronger. What is the reason for this? One reason, of course, is beneficial effect, which we have described already, that each contraction will reduce the viscosity in the skeletal muscle fiber. So sliding of the thin filaments becomes easier and easier. Another point that should be noted, the reason for staircase effect is there is increased availability of sarcoplasmic calcium. Increased availability of sarcoplasmic calcium. Let me just explain this here. This is a sarcotubular system in the skeletal muscle. It's a system of T tubules and L tubules. T tubules, the transverse tubules, and the L tubules, longitudinal tubules. A nerve sends impulse to the muscle. It crosses the neuromuscular junction. The impulse enters the muscle via T tubule. And then, as the impulse travels deep into the muscle, then it causes release of calcium from the tubules, the stored calcium, intracellular calcium. It's it's inside these tubules. It will be released into the sarcoplasm. Now, behind these tubules, there are those thin and thick filaments. So, this calcium will combine with troponin C on the thin filament, and that will initiate the contraction. We know this. Now, what happens is, see, for the relaxation to occur, there is a protein in this L tubule membrane called as Sarca, sarcoplasmic endoplasmic reticulum calcium ATPase. So, it will remove the calcium from the sarcoplasm and send it back, and the muscle will relax. This is how muscle contracts and relaxes. When impulse comes from the nerve, it enters the muscle, triggers the calcium release into the sarcoplasm, and then that initiates the thin and thick filament interaction. When calcium is removed from the sarcoplasm and sent back, muscle will relax. Now, if I stimulate the muscle 5 times in quick succession, what happens is there is a volley of impulses coming into the muscle, and each impulse is triggering the calcium release. So, calcium is getting released and released and released. Calcium is pouring into the sarcoplasm. So, what happens is, look, the calcium is also pumped out and the muscle is relaxing, but the rate of calcium going into the sarcoplasm is more. So, calcium starts increasing. Calcium levels begin to rise in the sarcoplasm. You have to imagine this, that there are quick impulses, let's say 10 impulses, 15 impulses, quick one after the other, and with each impulse calcium is going to be released. So, although calcium will be removed partly and the muscle will relax, but the rate of calcium going into the sarcoplasm is far greater. Therefore, calcium begins to accumulate, its level rises in the sarcoplasm. And the most important fact that I am going to mention now is that the strength of contraction of a muscle is proportional to the amount of calcium available in the sarcoplasm. More the amount of calcium in the sarcoplasm, stronger will be the contraction, better will be the actin mass in interdigitation, and therefore that produces stronger and stronger and stronger contraction, because calcium level is rising and rising in the sarcoplasm, right? So, that's a staircase effect. and its physiological explanation. In fact, what is the need to know all this? Let me just give you a slightly related example. What is the basis for performing warm-up exercises? Warm-up exercises, of course, we all know that the warm-up exercises which are performed just before the event, they will loosen up the muscles. Otherwise, a stiff muscle, and if you produce a contraction, there will be tearing injury to the muscle. Now, that is one role for the warm-up exercises. But the other possible explanation is that the warm-up exercises which are performed just before an event, actual event, just before that, if you perform the warm-up, there will be more and more calcium coming into the sarcoplasm. So the level of calcium in the sarcoplasm will be higher, and so more calcium available will produce a stronger contraction in the actual event when you actually need that for a 100-meter dash or a long jump or high jump or something like that. Means strongest possible muscle contraction needed for short time. But the point is, we are talking about frequency tension relationship, and stimulation frequency to the muscle was increased, and it gave us stronger and stronger contraction. When we recorded that on a rotating drum, we got this staircase effect. Stronger, stronger, stronger contractions. Let me just add one more point to this. If I stimulate the muscle with a very high frequency, let's say 30 times in a second, very high frequency was applied to the muscle, then what's the result? What do I get? I get the graph like this: muscle contraction, and then it remains in a contracted state. This is what I get. What I'm trying to say is, look at this graph. Muscle was contracting and then relaxing and then again contracting. Relaxation was happening. And look at this. If I stimulated the muscle at a very high frequency, the muscle contracted and remained in a contracted state. It is not relaxing at all. It fails to relax. So, a very high frequency of stimulation, the muscle goes into a sustained state of contraction. It fails to relax. This is called as tetanus, and the frequency is called as tetanizing frequency. So, tetanus is a sustained state of contraction, failure to relax, which happens from high frequency stimulation. Remember, whenever the word tetanus is uttered, what should come to your mind is high frequency stimulation of the muscle. Now, you must have experienced this in your day-to-day experiences as well. If you stimulate your muscle at very high frequency, for example, when we are writing an exam, a 3-hour exam, we toward the end there is a less time available and we go on writing very rapidly. What happens? We experience a stiffness in the muscle, sustained state of contraction. Muscle fails to relax and we have to wait for some time. We have to apply some pressure on the muscle. We have to wait, and then the muscle relaxes. So that sustained state of contraction was a physiological tetanus. Why did that happen? That happened because of a high frequency stimulation to the hand muscles. You are writing very, very rapidly. There was very high frequency stimulation to the hand muscles and they went into a sustained contraction. So that's a tetanus that we experience in our day-to-day life or routine scenarios of the life. Now, what is the physiological explanation to this? Look, we have seen this, that with each impulse coming from the nerve and causing release of the calcium into the sarcoplasm, for the relaxation to occur, this calcium has to be removed. This calcium has to be pumped out of the sarcoplasm. This calcium has to be removed and pumped out by this Sarca. When that happens, only then the muscle will relax. Okay, so calcium removal from the sarcoplasm and the muscle will relax. But imagine you are stimulating a muscle at a very high frequency, like 30 times in a second, very rapidly. With each impulse, calcium just keeps pouring in, calcium just keeps coming in, and there is no time for the calcium to be sent back. There is no time for calcium to be pumped out of the sarcoplasm. Before that, your next and next and next impulses are just coming in. So, no time for the calcium to go out of the sarcoplasm, therefore no time for the calcium, no chance for the muscle to relax. So, muscle contracts and remains in a contracted state. That's a tetanus. Therefore, this in short was the second factor which influences the strength of contraction of a muscle, the frequency tension relationship. But remember, up to a certain frequency, it's desirable because it will produce stronger and stronger contractions. But beyond that, a higher frequency would produce a sustained contraction. The muscle will not relax at all for some time, of course, but so therefore we must determine that frequency which is best suited for a particular type of event. Right. Now the third factor is load applied to a muscle. Load, application of load, how it influences the strength of contraction. Now let me make first statement. Remember, load opposes the muscle contraction. Load opposes the muscle contraction. So, if you apply the load, the strength of contraction will decrease. If you increase the load, if you increase the weight which has to be lifted, strength of contraction will go on decreasing. So, first point is load opposes the muscle contraction. So, in the same nerve muscle preparation which we are looking at, what we now apply is a load. This is the writing lever and a load is applied to it. Now, the writing lever has to lift this load. Muscle, when it contracts, it has to lift this load. Load will oppose the contraction, therefore strength of contraction will go on decreasing. Suppose I am recording these contractions with increasing loads. Suppose I go on adding the load here one by one. Gradually, progressively I increase the load applied to the muscle and I obtain the muscle contraction. One by one I obtain the contractions by increasing the load. The contractions will appear like this. Suppose this was 10 grams applied, then 20 grams, then 30 grams. So, what you can see here is I went on increasing the load, increasing the weight applied to this writing lever. It opposes the muscle contraction. So, contraction strength goes on decreasing. That is the first primary effect that you should understand, that load opposes the muscle contraction. Well, now hold on. I know what you're thinking. You will say that, sir, when the load increases, don't we produce stronger contraction? Yes. Let's not mix up the issues. This is an isolated nerve muscle preparation. And therefore, here the load will oppose the strength of contraction of the muscle. In the normal body, in the intact body, when the load increases, if we have to lift a heavy load, very heavy load, then we make a conscious effort, because see, that load is opposing the contraction of the muscle. So, we make a conscious effort from the cortex. We recruit more number of fibers in the muscle contraction and we consciously increase the strength of contraction. That's a different story. Okay. So, don't mix it up. Load will oppose the muscle contraction if it is seen in isolation, and strength of contraction will go on decreasing if you have increased the load one after the other. In the intact body, We know this already. Our cortex knows this already, that if you increase the load, it is going to oppose the muscle contraction, and therefore we make a conscious effort from the cortex. We recruit more number of muscle fibers in that contraction, and we increase the strength of contraction consciously by a conscious effort. That's a different thing. So please remember, these two are different things. But otherwise, load opposes the muscle contraction. It will decrease the strength of contraction of the muscle if seen in an isolated muscle. Coming to the same point, but slightly making a differentiation. Load is of two types: preload and afterload. So we need to understand this as well. Look, when the muscle contracts, suppose this muscle is well supported, we apply the load here in the writing lever. Now when the muscle begins to contract, I mean after the contraction has started, the muscle has to displace this load. So because the load has started acting on the muscle after its contraction has started, and the load is opposing the contraction, therefore all loads are basically after loads. All loads. I'll repeat myself once again. After the muscle contraction starts, the load starts opposing the muscle contraction. I mean, muscle has to displace that load, muscle has to lift that load, and load is opposing the muscle contraction. So because this load is opposing the muscle contraction after the contraction has started, all loads are basically after loads. And if I am plotting a graph of after load, it will be like this: increase the load and the strength of contraction will go on decreasing. Look, let me also explain. These simple muscle curves, they were recorded on a revolving drum. So I got a contraction followed by relaxation in the form of a curve. Whereas these graphs will be recorded on a stationary drum. I just apply the stimulus, I get a line like this because the drum is not revolving. So contraction, relaxation. So just one line. Then I manually move the drum forward, and then I apply the next load and then get the next contraction. This is how the graph is obtained. So this is on a stationary drum, and therefore contraction, relaxation. It will be just a line. Then move the drum, apply the load, again obtain contraction. So that's how this is obtained. Now basically all loads will be after loads, as I mentioned. But some loads are preloads. What is the meaning of that? Well, I have already explained this concept in another video in my channel. How many types of what is the load against the muscle? So you can just go through that video again to understand these concepts little more further. But what is preload? Pre means before. So when load starts acting on the muscle even before its contraction has started, that is called as preload. Remember, before the contraction has started, the load started acting on the muscle will be called as preload. Imagine this. Suppose this muscle is unsupported. The muscle is unsupported, not supported at all. And I apply the load. You know what will happen? The muscle is resting, it will be stretched. As soon as I apply the load, the muscle will be stretched. And then I stimulate the nerve muscle preparation, I apply the stimulus. Then the muscle contracts and it has to lift the load. That's a usual story. We know when the muscle contracts, it has to lift the load. So load is anyways acting on the muscle when the muscle contraction starts, and therefore contraction has to lift and displace the load. That's a given thing. But in this case, load started acting on the muscle even before its contraction started. I'll give you an example, or just a similar type of example, that suppose you are lifting a bucket from the ground, and you are going to lift it with biceps. You are going to lift the load with biceps. But imagine that you are lifting it from the ground and just holding it like this, holding the bucket. Can you imagine that now the load has stretched your biceps? Biceps is not started to contract yet, just biceps stretched. That means the load has acted on the biceps even before its contraction started. Biceps contraction will be this. You have not done that. Just lifted the load from the ground and standing. Biceps got stretched and stretched in its resting state. That means this will be preload. Now, preload is beneficial up to a certain extent. Why? Because preload applies the Starlings law. You know, as you lift the load, or rather, as the muscle is stretched, in its resting condition, the muscle was stretched. And then when the muscle contracts, it is going to lift the load. That's a normal story. Load will oppose the contraction. But then, since the muscle was stretched in its resting condition, the muscle length was increased in the resting condition. Muscle fiber length increased, sarcomere length increased, and we all know that increase in the length, stronger is the contraction within physiological limits, is the Starlings law. So, preload is slightly more beneficial in that sense that it will generate stronger contraction. Up to a certain physiological limit, it will produce stronger contraction by Starling's law. So, this was the after load. Then preload graph would be something like this: 10, 20, and what I am showing here is the baseline has gone down little bit because muscle was not supported, and therefore as you apply the load, the muscle gets stretched and the writing lever goes down slightly, and the contraction will start from that line. So 10, 20, 30, and then physiological limit is exceeded. But what you can observe is you are applying the load, height of contraction is actually increasing. Why? It's a stronger contraction by Starling's law. That's a preload, and that's the effect of load on the skeletal muscle contraction. Next factor that influences the contraction is fatigue. If I stimulate a muscle continuously, so first of all, what is a fatigue? Inability to respond normally is called as fatigue. So, repeated stimulation of a muscle for prolonged periods, and what happens? The strength of contraction will go on decreasing. Strength of contraction goes on decreasing and muscle is going into fatigue. If I have to record it graphically, well, remember when we discussed that staircase effect and tetanus, there was high frequency and short duration stimulation. So, for a short duration, we stimulated the muscle at very high frequency. Whereas here I am saying that the muscle will be stimulated slowly at a very low frequency, but for prolonged periods. And if I record the graph will be like this: repeated contractions recorded on a revolving drum again. So, we get a simple muscle curve. After initial contractions, then slowly the contraction strength will go on decreasing and the graph will be like this. So, you can see the strength of contraction decreasing, muscle going into fatigue, inability to respond with a normal strength. This is the factor that influences the strength of contraction. So, your athlete, your sports person will want to know what is his fatigue time, when the muscle goes into fatigue, and what factors he can observe so that the fatigue is prolonged or delayed. I mean to say, fatigue is postponed. So all these things we should be keeping in mind. First of all, let's see the physiological principle behind it. Or you can see this part also. Let me just explain quickly what it is. It's sometimes called as contracture remainder. Contracture remainder. See, contraction started from this line and relaxation means it has to go to that line. Contraction of the muscle and relaxation, the muscle lengthens completely. This is a normal muscle contraction and relaxation. What you can see here is that during fatigue, muscle is contracting with a less strength, so height is less and less, and relaxation is not complete. I mean, the graph has not gone down to its normal baseline. Muscle has not lengthened completely. So writing lever does not come down completely. It remains up. So that means some amount of contraction has remained in the muscle. Muscle could not relax completely when it is going into fatigue. That's called as contracture remainder. Look, ATP gets exhausted when the muscle is getting fatigued. And after the exhaustion of the ATP, all the myosin heads will not be able to detach from the actin. So there will be some amount of actin-myosin tethering that will happen even after the muscle relaxes completely. So that's a contracture remainder, and this is another factor that influences the strength of contraction. What is the explanation for fatigue? Look, if you go on stimulating the muscle continuously, repeatedly, one after the other, this is a nerve trunk and this is the muscle that it supplies. These are the nerve fibers and these are the muscle fibers, let's say. This is just a diagrammatic representation. Now I am stimulating the nerve and the impulses are sent by the nerve into that muscle. Those are the muscle fibers. Just a diagrammatic representation for explanation. With repeated stimulation, what is going to happen is, in each of these neuromuscular junctions, the acetylcholine will be exhausted one by one, one by one, one by one. In those neuromuscular junctions, the acetylcholine will be finished. So suppose first this fiber, its neuromuscular junction, acetylcholine is finished. This fiber will stop contracting. It will not contract at all. So we are left with only three fibers to contract. Then this fiber exhausts its acetylcholine in the neuromuscular junction. So that fiber stops contracting. So in this manner, acetylcholine is exhausted, neurotransmitter is exhausted, and therefore therefore those muscle fibers stop contracting, and therefore strength of contraction goes on decreasing in this manner. So exhaustion of the acetylcholine in the neuromuscular junction. Remember, therefore, this is very commonly asked, what is the seat of fatigue? So remember, nerve does not ever fatigue. Muscle also indefatigable, means muscle also does not fatigue. You know, after this experiment, if you stimulate the muscle directly, muscle contracts. So it shows muscle by itself does not ever fatigue. Nerve does not fatigue. So what fatigues? The junction between a nerve and a muscle. That's neuromuscular junction. That is the seat of fatigue. And what has been finished? The acetylcholine, which is released in the neuromuscular junction. That is another factor. Now, last two factors are just related to each other. Number of motor units in a muscle, and the last factor will be number of muscle fibers in each motor unit. So let us define the motor unit first. What is a motor unit? Motor unit is a single motor neuron, all its branches, a single motor neuron and its branches and all the muscle fibers supplied by that motor neuron. That makes a single motor unit. Let me just draw a diagram. Let us represent this diagrammatically. Suppose this is a nerve. Nerve is a nerve trunk and there are nerve fibers in that nerve. These are the nerve fibers, the axons, and this is the muscle that it innervates. This is the entire muscle. Just a diagrammatic representation. Now, this one single motor neuron and its branches, let's say these are the three branches of that motor neuron and the muscle fibers supplied by those branches, that makes one motor unit. So, these three muscle fibers are supplied by this number one motor neuron. One single motor neuron, its branches and all the muscle fibers supplied by that. That is one single motor unit. Now, let me explain. Let's just first draw all the motor units in this muscle. This is another axon or another nerve fiber. Its branches, let's say 4 muscle fibers were supplied by 4 branches of that axon. And let's say another motor neuron. See, this is the entire nerve trunk. It contains all these nerve fibers in it, the axons. Each axon has its axonal branches and those branches are supplying the muscle fibers. So, let's say 3 muscle fibers in this particular motor unit. So, we have 1, 2 and 3, 3 motor units in this particular muscle, and in all 3 plus 3, 6 plus 4, 10 muscle fibers. This entire muscle has totally 10 muscle fibers. Just for the sake of understanding, we are taking as an example 10 muscle fibers, but we are looking at the motor units into which those muscle fibers are segregated, separated. Now, I need to tell you two things. One is, a single motor unit obeys all or none law. Remember, if I may just repeat once again, what is a motor unit? A motor neuron, its branches and all the muscle fibers innervated by it. That makes a single motor unit. Now, a single motor unit obeys all or none law, all or nothing principle. All or nothing principle means either all the fibers in that motor unit will be contracting together or none of them will be contracting. See, there is nothing, there is nothing in between. So, a single motor unit obeys all or none law. If this nerve fiber has been stimulated, fiber number 1, then it will send impulse to all those 3 fibers and all the fibers will be contracting. And if your stimulus was not good enough to excite this nerve fiber number 1, then no impulses to those 3 fibers. Those 3 fibers will not contract at all. That motor unit will not contract at all. So, a single motor unit obeys all or none law, all or nothing principle. But entire muscle does not obey all or none law. Entire muscle, this entire muscle will not follow all or none law. What do I mean here? there is a principle called as recruitment of motor units. Recruitment of motor units. So, if I apply a weak stimulus and it just stimulates one motor unit, or rather one nerve fiber stimulated, so only these three fibers will be contracting. Those three fibers will be contracting, and a weak contraction of the muscle. If I increase the stimulus strength further, for example, I gave you the example, if I increase the load which has to be lifted, the stimulus strength coming from the cortex is increased to the muscle. Cortex sends a stronger signaling to the muscle. So now, two nerve fibers will be stimulated, because a stronger stimulus has been coming from the cortex, because cortex has recognized that the load has increased and therefore you need to produce a stronger contraction. So two nerve fibers, and that means two motor units will now come into contraction. So these three fibers plus second motor unit having 4 muscle fibers, 3 plus 4, 7 muscle fibers contracting now. Contraction will be stronger. If the load is increased further, now you need an even stronger contraction. Now cortex will send even stronger stimulus into the muscle. So 1, 2, 3, all 3 nerve fibers will be excited going to that muscle, and therefore even this motor unit, the third motor unit, will be recruited in the contraction. So this is called as recruitment of motor units. They will be recruited into the contraction, and therefore contraction can become stronger and stronger and stronger. And this when all motor units are contracting in this muscle, that will be the strongest possible muscle contraction, obviously, because all motor units have been recruited. Muscle contraction cannot become stronger than that. So remember, but what we have said is a single motor unit will always obey all or none law. Means all the fibers in a motor unit will either be contracting together, all of them, or they won't be contracting at all. None of them will be contracting. So, and it depends on whether the nerve has been excited with a threshold stimulus, so that it sends signals to all fibers and all fibers contract, or there is no threshold stimulus and no signal going to the muscle fibers in that particular motor unit, none of them will be contracting. But entire muscle did not obey all or none law, because there were one motor unit contracting, then 2, then 3. It was like that, recruitment of the motor unit. So this is another physiological principle that governs the strength of contraction of a muscle. Recruitment of motor units, it can happen with stronger stimulation, stronger and stronger and stronger stimulation going from the cortex. So remember, if you need to increase the strength of contraction, by training you have to know how strong is the stimulus that your cortex sends to the muscle, so that more and more motor units will be recruited in the contraction process and strongest contractions can be produced. So these are the factors that govern, influence the strength of contraction of a muscle. Let me just add the last factor, number of motors. Summarize this last 2 factors. Number of motor units in a muscle, this will govern the strength of contraction. So see, if there are more number of motor units in a muscle, muscle contraction will be obviously stronger. More fibers will be contracting at a time. And last factor was number of muscle fibers in each motor unit. Look, motor unit size is not fixed. I mean, some motor units are very small, like motor units in the extraocular muscles of the eyeball, with only 2 muscle fibers. Whereas Some other motor units like that of the muscles of the back, muscles of the thigh, they have large motor units with 100 muscle fibers. So, size of the motor unit means how many fibers are there in each motor unit, and how many such motor units are there in the muscle. So, imagine each motor unit has only 2 muscle fibers, and suppose there are only 4 such motor units. So, totally 8 muscle fibers are there in a muscle. It will produce a certain contraction, and suppose in each motor unit there are 50 muscle fibers and there are 10 such motor units in that muscle, then 500 muscle fibers. That means contraction would obviously be stronger in the second muscle. So, number of fibers in each motor unit and number of such motor units in that muscle, these will govern the strength of contraction of a muscle. So, that was the summary of factors influencing strength of contraction of a muscle.